Physics Lab 1 by Siddardh Budamagunta. An overview. The purpose of this lab is to prepare charged pieces of clear tape and observe the interactions between these charged pieces of tape, and to conduct an experiment that determines the excess amount of charge on the tape, and model the interactions using VPython. Here are the overall results. First, some physical principles. Coulomb's law is used to determine the force between two charges. The electric force between two charges is equal to the Coulomb's constant K times the value of the first charge and the value of the second charge, all divided by the distance between the charges squared. This is then multiplied by the r hat vector to provide the direction of the force. When the magnitude of the force is needed, then it's not needed to multiply by the r hat vector. Additionally, I'll be using the gravitational force using Newton's second law, and considering that the acceleration of Earth's gravity is 9.8 meters per second squared. I'll also be considering net forces, and the net force on an object is equal to the vector sum of all the forces on the object. By Newton's second law, if the net force is equal to 0, then the acceleration is 0. Materials used in this lab are clear tape, ruler, flat surface, 2 books, and a plastic pen. For the first experiment, I make 2 pieces of tape, a base tape, which I place on a flat surface, and then another piece of tape, the U-tape, which I place on top of the base tape. If I quickly pull the U-tape off the base tape and place it on the edge of the desk and bring my hand close, I can test the attraction of the tape. In experiment 2, I make 2 more U-tapes like previously done. I test the interaction between the 2 pieces of tape by bringing them closer together and observing what occurs. Lastly, I rub the pen on my hair to negatively charge it, and then bring it close to the U-tape to test its charge. In experiment 3, I make 2 more pieces of U-tape. I put 2 books a small distance apart, and then place the piece of U-tape across the gap. I take the other piece of U-tape and bring it underneath the first piece of U-tape. And then I bring it closer until the electric force is enough to cause the first U-tape to move upwards, and then measure the gap between the 2 pieces of tape. When I first brought my hand near the charged piece of U-tape, the tape moved towards my hand. When I charged the 2 pieces of U-tape and brought them closer to each other, I expected them to repel, and this is what occurred, which makes sense since they probably had the same charge. On the other hand, when the U-tape was brought near a neutral object, it attracted towards the object. When I brought the negatively charged pen towards a piece of tape, it attracted to the piece of tape, suggested that the U-tape is positively charged. When I performed the experiment to determine the charge of the U-tape underneath repelled the U-tape attached to the books. The repulsion was strong enough to raise the middle of the U-tape above the edges. I measured the distance between the lower U-tape and the U-tape above it, as it could be helpful in the calculations for charge. Some assumptions that make it easier for calculations. I assume that the tapes are actually point charges. This was necessary as it allows for the more simple use of Coulomb's law. I assume that the tapes had equal charges. I assume that the tape is 1 atom thick. I assume that the mass of the tape was 1 gram per meter of length, and I assume that there are only vertical forces in the third experiment. It's helpful to have context that the calculations can be made within, and so I made a created body diagram. As you can see, this is the top piece of the U-tape, and on it are the force of electricity and the force of gravity. And since this tape experiences no acceleration by Newton's second law, the system is experiencing 0 net force. And this suggests that the force of gravity and electric force are equal and opposite. And on the right are some of the constants that I use in the calculations. So first, I decided to calculate the force of gravity on the tape. And since the net force had a magnitude of 0, I set the magnitude of force equal to the magnitude of the force of the magnitude of the force of gravity equal to the magnitude of the force of electric force. And then I plugged in the values of the known constants and calculated values and solved for the value of the charge. I then used the calculated charge value along with the number of atoms in the tape to determine the fraction of atoms that gave up an electron. When the final experimental results are compiled, the charge of the tape is positive, the charge of the tape is 8.4 nanocoulombs, and the fraction of the atoms that gave up an electron is 1.38 times 10 to the negative 7. So code in VPython, this is the code I use to produce the model. On the left are constants, functions, and the tape values, and the right are calculations and visualizations. So this is the final model and results. As you can see, I represented the tape as 2-point charges, and on the top piece of tape, there are the equal forces of gravity and electric force, but in opposite directions. Below are the calculations model. The discussion, key takeaways, charged tapes both have a positive charge, both the experimental and Python model produce the same final results. Sources of error are human error from inaccuracies in measurements, from both tape size measurements and measurements in distance between tapes. The assumption that the top of the tape only experienced vertical forces when it was attached to books is another source of error. If electrons had positive charge and protons had negative charge, most of the observations would still stay the same, since the tapes would have a negative charge instead, but they would still repel, as they have like charges. The main difference is that electron deficiency would lead to a negative charge rather than a positive one. It's important to handle the charged tapes as little as possible, because each time it comes into contact with our